and so on. So, brief outline of this talk. So, I'll basically start, like the main topics of this talk will be photometry and spectroscopy of star clusters, and you'll realize through the talk that I'm kind of biased towards globular clusters since they are more related to my own research. In the end, I want to kind of combine photometry and spectroscopy to integral field spectroscopy. Who has heard, just out of curiosity, who has heard of integral field spectroscopy yet? No one? Okay, then it's good that I give a hopefully broad introduction to it. And the lecture will close with something where you actually have to work yourself, because one idea of this school was, also to prepare observing proposals. And one thing you want to know if you prepare your observing proposals is how much exposure time do I actually need on a telescope. And exposure time these days is quite precious, so we need to estimate it quite accurately. And this will be the end of this lecture. Throughout the talk, I try to make it interactive. And also, if you have any questions, don't hesitate to interrupt me, since after all, this is for you to learn something. So, if there's anything unclear also, just ask. Let me start with recalling some of the things that we've seen in the last lecture. And one major aspect of the last lecture was about the color magnitude and Hertzsprung-Russell diagrams of star clusters. So we've basically seen, mainly in Randa's lecture so far, the Hertzsprung-Russell diagram, where you basically plotted temperature on the x-axis and the luminosity of a star in the y-axis. Now, both the temperature and the luminosity of a star, they're not really easy to measure, because what we usually do when we do photometry is that we measure the brightness of a star in certain colors. And so the color magnitude diagram, what is it actually? It's basically what you see here. It's that you plot the color of a star, so in this case using two filters, V and I, against the brightness or the magnitude of the star in one of the colors. So this is a color magnitude diagram. But what you actually see here is the same what you see in the Hertzsprung-Russell diagram, that basically temperature increases from right to left. So the bluer a star appears, the smaller its color in V and I will be. And the brighter a star is, the lower its magnitude gets in V. And so maybe we can do this also now interactive. So what can we actually learn from such a color magnitude or Hertzsprung-Russell diagram? So you've hopefully learned some of the aspects that we can get on it for star clusters in the last lecture. So anybody has still an idea what we can learn from this color magnitude diagram? Nobody? Nobody except for the lecturers?
Again, please. Your question?
Starts with an A.
So,
Again, your question?
So basically, I'm dealing now with the second question down here. What can we learn from this type of diagram about a star cluster?
Qu'est-ce qu'on peut obtenir?
So this will be a long lecture if you don't participate. So unless you, if you want to have lunch at some point, you should now really.
Just one moment. You can explain what V minus 1V, what's meaning X and Y axis?
So or maybe
What is it?
maybe that wasn't quite clear in the last lecture. So. Okay, so what Randa showed you was always, she plotted, this doesn't work, this is better. So she plotted the luminosity of a star
Yes.
and the temperature.
Yes.
So this is the temperature of a star, and it was basically the logarithm of the temperature. And you basically had the main sequence going this way. Now, what you usually do is, if we look at some of the spectra, where we have wavelengths and where we have the flux of a star, then a blue star looked like this, like a hot star. A star with a high temperature looked like this. And a star, so let me actually, to get this right from the beginning, let me show you this in blue. So a blue star has a high temperature because it has a lot of flux in the blue and less flux in the red. So if we have a red star, it will look like this. Not so much flux in the red, a lot of flux in, not so much flux in the blue, a lot of flux in the red. But what we do when we do photometry, we observe a cluster through certain filters. Like in this case, there's a V and an I filter. And what these filters do, they basically let you collect the light in certain wavelength regions. So this is the curve, this is the filter curve. So the wavelength range in which a filter is sensitive. So for example, this would be the V filter. And you see that the blue star has a lot of flux in the V filter, and the red star doesn't have much flux in the V filter. The second filter we looked at is the I filter, which is at a larger wavelength. And you see that here it's the other way around. So the red star has a lot of flux in the I filter, and the blue star has not so much flux in the I filter.
I filter is red filter?
I filter is, in this case, it's kind of a red filter.
Okay.
And yeah, V is kind of visual, so it's sort of blue.
Or blue. Blue.
So it's a blue and a red filter.
Okay.
And the thing about this this color magnitude diagram is that stars in this region of it are blue, and stars in this region of it are red. So we have red stars in this region, and blue stars in this region. And so in a way you can again see this as a temperature. Red stars have low temperatures, so they're here. Hot stars have blue temperatures, so they're here. And then the V filter basically here. The brighter a star in V, the more it will be up here. So in this case, this is again the luminosity of a star. So basically what we see there and what we observe in this diagram of luminosity against effective temperature is basically the same thing. So is this more or less clear? So then let me come back to my question. What can we learn from this kind of diagram about a cluster?
You can't take a classification of the star.
Exactly. So one thing we could do is we could look at, so each point here is an individual star observed in a globular cluster, and for example, from looking at its color, we could get its temperature and hence its spectral type.
Much of these stars in the clusters in the middle, that's not a lot of red or blue.
You don't see many blue stars here, that's right.
Not many, yeah, a little more than
So,
red.
but
They do not go very high.
so just maybe we can go one step back and look at the. Can you identify the main sequence here? Or
Yes, we can.
where? So can anybody point at the main sequence here? Who wants to point at it?
In this
Or-
line, in the same line, it's a line of stars. It is, يعني from the high left, high right to lower left. This maybe main sequence.
This one here?
No. This line. Up. يعني
So you can't.
maybe it's, yeah, this. This maybe.
But what did we learn about the main sequence? It's going to higher temperatures and so it's going to higher temperatures and higher luminosities. So it should go something like this. So
But I see this V 22 to 12. It's,
yeah, so up here that's luminosity, and temperature increases from here to there.
I turned this one.
yeah, this.
No, it's.
This one. I turned this one 6 minutes from her.
But this doesn't go the right way, right? So this goes up and to lower temperatures.
No, so temperature is increasing from here to here.
Yeah, it's the same like with the Hertzsprung-Russell diagram that Randa talked about. Temperatures are lowest in the red part and highest in lowest in the right part and highest in the left part.
But we don't say any main sequence here.
Yeah.
If we
Then here. Here is the low temperature.
Yes, there's a low temperature, right? Yes.
Low temperature, that means, as Dr. Randa said, it will be moving in this line.
Exactly.
Okay,
Yes.
there is any stars in this line.
Well,
Except here.
Yeah, exactly.
This, just
Yes.
this very, very small amount of stars here. This, yeah, maybe normally the same.
So yeah, but exactly. So this what we see here is this is the main sequence.
That's little.
It's that's one of the problems we have, that we cannot observe all of the stars usually in a cluster. So because some of the stars are just so faint that we don't see them. Okay, so we've identified the main sequence, which is this part here. Now what's this part here?
This sequence. Red giant.
Exactly, that's the red giant branch, yes. And finally you see this part here.
This blue giant, I think. Oh,
You see it looks kind of horizontal here.
this want to go to the white dwarf?
This is the horizontal branch that Randa talked about, where stars burn helium in their cores.
Yeah.
This is when stars end up
Yellow
here.
giant. Yellow giant.
So it's called horizontal branch. So these are horizontal branch stars that you see here. So we have the main sequence, then we have the turn-off here, we have the red giants, and we have the horizontal branch. There. So like what you learned about in the previous lecture is, at some point, you know, the stars move up the red giant branch. Until this point here, they burn hydrogen in the shell.
Okay.
And at some point, you have the ignition of helium burning in the core,
Okay.
which is called this helium flash, and which makes the stars move in this part.
Helium flash, yeah.
And this is called the horizontal branch. And this is what you see here in, this is the horizontal branch. So
That in yellow giant, Dr. Randa name it. As I see, you can go back to them. Maybe it's names. No.
yeah, but yeah, usually they are referred to as horizontal branch stars.
That's name, horizontal branch. Okay. Now we have three age of stars in main sequence, red giant and horizontal branch.
Exactly.
Same global cluster.
Yes.
Good.
So, so now, can somebody tell me what can we learn from it?
They goes to die.
If we look at something like this, what does it tell us about the cluster? Yeah,
The age.
exactly. One thing that it tells us is the age. Since we can look at the turn-off, and we see that, you know, all up here, there's no main sequence anymore.
Yeah.
So all of those stars have died already, so it must be a very old cluster.
Yeah. About size, maybe we can talk about size?
I mean, yeah, looking at how many stars there are, you could also infer something about how big the cluster is. That's also possible. What one could also look at is the distance of a cluster, because if the star is further away, then all the stars appear fainter, so this whole thing would move down. And you can also learn something about the chemical composition of a cluster. And this is what I want to illustrate you here. So let's look again at two stars. One is a horizontal branch star and one is a red giant star, and both have approximately the same magnitude. Can you tell me which star has which spectrum?
We need the temperature. High temperature.
So this is wavelengths down here and this is flux.
Yellow gene, the blue one? The red gene, the blue one.
Exactly. So it's already indicated by the colors. So the blue star is hot, a lot of flux in the blue part. At short wavelengths, the red star is cold, so it has more flux than the blue star in the red filter. So this is the I-band filter curve and this is the V-band filter curve. And to illustrate why, we can also learn something about the chemical composition. What you see here, you see all those spectral lines, and in the red star you see that you have a lot of spectral lines here. And this is for a star with a low metallicity. So the star hasn't many iron elements inside it, so these stars are rather weak. But if we would have a star with more iron elements, you see that all the lines get much stronger. And this will also affect the color that we measure and the brightness that we measure. And in a simplified way, if the metallicity content of the stars would increase, they would kind of move in this direction. So they would kind of become, sort of redder and a bit less luminous. And the reason, for instance, why they become redder is that you see that most of the strong lines are in the blue part of the spectrum. So we have more absorption in the blue part of the spectrum, so the spectrum and the star color will appear redder. So this is kind of why color magnitude diagrams are so important for cluster research. And if we look at a typical globular clusters inside our Milky Way, this is 47 TAC, which is one of the most massive globular clusters in the Milky Way, which has approximately 1 million solar masses of mass. So it's really quite massive. And this is how the color magnitude diagrams that we could observe for these clusters have evolved with time. And you kind of see here again the problem that we also had is that in the first color magnitude diagrams, you could barely see the main sequence. You only had this very, very short main sequence here. But then, you know, when our techniques became better, like when we went from photoplates to CCDs here, you see that we could finally look at the main sequence in much more detail. And this was just because we got better instrumentation and better analysis methods.
It's not come from science or something like that. Just we don't have the power CCD to give the high.
Exactly. So when we got the first data for the globular clusters, most of the faint stars were just not visible because our detectors weren't strong enough.
Yes.
And our instruments were big. Our telescopes weren't big
But
enough.
you don't have an idea about after 1987.
I do. This is how it looks today. So this is taken with the Hubble Space Telescope, to which I'll come in a second. And what you can see here is, look at this main sequence that you see here, and compare this to the previous ones. It's much clearer, and it actually goes all the way down to the stellar mass limit, so to the lowest stars that we have in the cluster. And what's also nice is what's a bit of a coincidence is that 47 Tac is close on the sky to the small Magellanic Cloud. So you also have the main sequence of the Magellanic Cloud in here. And you see a third sequence here. Does anybody know what this could be? What happens after the stars have ended their lives is they cool down here and become white dwarfs, exactly. And what we see here is how the white dwarfs cool down. So, you know, thanks to instruments and telescopes like Hubble, we're now in a situation where we can look at all of the stars, no matter how faint they are in a cluster. So, and this is a picture of Hubble, which has really changed how we look at globular clusters and star clusters in general today. And it's a satellite, so it's floating around in space. And one nice picture that was once taken is when they serviced it, is here you have Hubble flying over South America, and here you see the Atacama Desert. And some of you may know that a lot of the large telescopes are situated in Chile in the Atacama Desert. And for instance, this is where the Paranal Observatory of the European Southern Observatory is located. And the Very Large Telescope is one good example for modern, huge ground-based telescopes. It consists of 4 main telescopes that you see here, and all of those inside the domes have a mirror with 8 diameters, with 8 meters of diameter. And I will use, throughout my talk, I'll use Hubble and the Very Large Telescopes as examples for modern instruments that we use to look at star clusters these days.
I have a question. So you don't have the prediction about the score, how will the score using the James Webb Telescope in the future? Just prediction, so...
I didn't look at a prediction so far.
Because now we know how the James Webb Telescope, the magnitude that can measure, and then we can predict this...
So I assume that Hubble, the James Webb Space Telescope, will again push this to even higher precision, and also the advantage is that we'll be observing in the infrared and not in the optical part of the spectrum.
Yes.
So it will give us again a lot of information, I think. So, so this and now I have one type of observatory that's in space, Hubble, and one type of observatory that's on the ground, the VLT. Does anybody have an idea what the advantages and disadvantages of those type of telescopes are? Yeah.
Calibration.
Calibration in what sense?
Disadvantage.
Yeah, that's one disadvantage that, like for which type of?
Energy, if you have problems with data,
Yeah.
so and energy, you need to make energy calibration. You can't go there and do it.
Exactly. That's one big issue that you have when you go in space. That the things are in space and you cannot reach them anymore.
I think for advantage we can say a lot of more detail about the space, so it's for the science, for including science, and for the disadvantage, you have to put a lot of money to do that, maybe, I don't know.
Exactly, so space missions are also much more expensive. So they're very expensive, and calibration is a very big issue, and if something breaks you have a huge problem. Why do we go to space nevertheless? Exactly. So if we observe from the ground, we have to look through all this atmosphere that surrounds the Earth. Obviously, the atmosphere is what makes us able to live on the Earth, but you know, being an astronomer, you sometimes want to turn it off, at least locally over your telescope. Oh, sorry, wrong direction. So the advantage is clearly that we have no atmosphere, and the atmosphere that we have no atmosphere, for instance, helps us in that we have no night sky, so we don't have any nearby or faraway cities that pollute our light. We have no absorption, for instance, the atmosphere of the Earth is opaque at a lot of wavelengths. And we're just lucky that in the visible part of the in the visible part of the spectrum that you see here at about 0.5 micrometers, the atmosphere is transmittive. And then there's a huge transmission window also in the radio regime. So that's why we have so many radio telescopes on Earth, because we can look through the atmosphere. But for example, if we want to observe in the X-ray regime, which is here, then we cannot do this from the ground because the Earth's atmosphere just doesn't transmit the X-rays. Which, looking at the X-ray spectrum of the Sun, is actually a huge advantage for human life. So that's quite good. And the disadvantages, as we already mentioned, it's very expensive. You're very limited in the instrumentation that you can have in space, because also maintenance is very difficult. And I found this cartoon, which I quite liked a lot, of the new Hubble in space getting like an eye surgery or getting contact lenses. You know the story behind this? It's when they prepared the mirror of the Hubble telescope, they actually made a mistake, and the mirror had the wrong shape when they shot it to space. And then they had the issue that they had this huge mirror in space, and they got images that were unsharp and that looked blurred. And so they basically had to send up a space shuttle and insert some correction optics to get sharp images with Hubble. Yeah.
In space we can observe it every day.
Exactly, that's also an advantage. You don't have really a day and night cycle, but you can continuously
I
observe.
want to ask about the Q. How many days you need to use the Hubble or this? There is many, I think you need long time to use the Hubble telescope or you. I think that.
Yeah, so that's in general a problem of modern instruments, is that people always ask for a lot more time than is actually available.
Long queue.
So
Very long queue.
it's very challenging to actually get observing time. So and I think that's also why it's important, to give you an idea of how to write observing proposals during the school, so that you have an idea of what you have to take into account when, for example, you want to observe with Hubble and it's very challenging to get the data. And you have to write a good proposal to get the data. So I think this is also one of the ideas of this school. So.
Do you know some proposal accepted for James Webb Telescope for cluster star? I say we have 13, but I don't know if...
I mean, so the first round of James Webb proposals, they just made the selection, and there's one globular cluster that they're going to observe, M92. So not terribly much science on stellar clusters so far, but it may change. So. Okay, so keep pressing the wrong buttons. Great. But why is it actually one other big advantage of why we want to go to space is that space gives us a higher spatial resolution. And to illustrate you why this is, let me illustrate you what a telescope does. So maybe you still know from your optics lecture what happens, if you have a light source, like in our case a star, and then put, observe the pattern behind a pinhole. Only that in our case the pinhole is a telescope. And the diameter of the pinhole is the diameter of the primary mirror. So we have a huge pinhole through which we observe the light of the star. And what you observe then is that behind the pinhole these planar waveforms will be bent, and on your detector you will then observe a diffraction pattern, which is caused by the reason that, for instance, in the center of your detector, light traveling from both sides of your aperture, or our telescope in this case, have the same pathway. So you have constructive interference here, but if we move away from the optical axis, you see that the light traveling from one part of your mirror has a longer way to go than the light from the other part of the mirror. And if this difference in path length, dx, I label